Ladies and gentlemen, you may ask yourself, why do we need a visiting professorship? You know, we are all, not only due to Corona, but we are all networked. We are all the time online. We talk to a lot of people all the time. Why do we need another Kurt Gödel Visiting Professorship? The Faculty of Informatics of TU Wien really wants to further enlarge its international outreach, to further have internationalization on the really high level, excellence level in all different areas where we are known for, be it in logics, be it in visual computing, be it in computer engineering, or be it in information systems engineering. So we thought that we wanted to have a close collaboration with internationally renowned computer scientists and this almost sounds now cynically in times of COVID, to bring them to Vienna, to work together with them, to have them work with our students, and to, by this, enlarge our outreach also to other internationally renowned universities. COVID was a little bit not part of the plan, but I'm very happy and I'm really proud that we, although there is now the pandemic, that we managed to convince an internationally renowned scientist to really accept our invitation for being our first Kurt Gödel Visiting Professor. Frank Leymann, I guess most of you know him. You know him from either People, the business process execution language. You know him from the workflow suite from IBM. He was chief software architect for more than 20 years at IBM. Or you know it from all his work on cloud computing, cloud patterns, how to develop and modernize cloud applications. But what you perhaps not know, that he is doing a lot of work in quantum computing over the last years. And why? Perhaps you have to study physics and mathematics, that you, after having done 20 years or 30 years of software development, that you say, wow, there is something more than traditional algorithms. And so he kind of developed an own research area in his research team at the University of Stuttgart. And I'm really very happy that we could convince him to come to the TU Wien and by this build up here a new research, kind of a new research area and a new research team. You might know TU Wien has one of his research foci, quantum technology and engineering. And we are really delighted that with Frank Leymann, we could convince a computer scientist to kind of stand up next to the mathematicians and physicists to really build up this real interdisciplinary area. Frank, I'm very happy that you are at least virtually among us, and it is your floor.
So again, thank you very much, Gerti, for the very kind introduction. And really, I'm looking forward, if the pandemic situation is over, that I visit, as you and I planned, for up to 3 months per year, TU Wien, and then work with the colleagues over there that are interested in quantum computing. So today's talk is titled The Power of Quantum Computing. And what I want to do is I start my talk with the well-known Moore's law. So you know that Moore's law says that the power of CPUs is doubling every n month. And if you really take a look here, and now I can't scribble because I don't have my iPad here logged in for what reason ever, it begins to be an S shape. That means it is saturating for a to a certain degree. That basically means that the components on the chip really get closer to the size of an atom. And this basically means that this limits classical computers, because quantum mechanics at the sudden determines the physics of computers. So you need to move towards quantum computing. The other observation is that there are domains that require a constant increase of compute power. For example, the CEO of AMD reported a couple of months ago that AI applications require the double processing power every 3.5 months. So if you take AI, especially machine learning, serious, you need an increasing number of compute power. That means without quantum technology, and here now the first bullet comes into the game, without quantum technology, IT support will remain at the same pace, at the same level that we do have today, which is for many applications unacceptable. And finally, there are a bunch of quantum algorithms that often show a significant speed up, as well as a much higher precision compared to classical algorithm to solve problems that are classically impractical to solve. And there are even already problems identified that are impossible to be solved on a classical computer. So this is the third theoretical argument to move towards quantum computing. So here's an example of, or here are examples of sample speedups. For example, in a classical world, if you have a bunch of coins and you want to toss them to find out whether these are bogus coins, that means the two sides have the same symbol, or whether they are correct coins, right? If you have n coins, you need to throw at most half of them. But in quantum computing, you only need to toss them once, which is an exponential speedup. We will briefly sketch the idea how to exponentially speed up factorization. That means the factorization of numbers into prime numbers, which is at the heart of our current security infrastructure, right? There is an algorithm that I'm discussing briefly, Shor's algorithm, that does it exponentially faster than the best well-known classical algorithm. There are speed ups that are not exponential, but they are speed ups. For example, in unstructured search, if you want to search, for example, a telephone book, you only have a phone number, and you want to find out the name of the person with this phone number. You start at the beginning of the phone book, and then you go through to its end, right? You need at least 1/2 + 1 lookups there. In quantum computing, you do it with the square root of n, which is quadratic speed up. There's speed up in simulation technology, molecule simulations, which is based on an exponential speed up of determining eigenvalues. There is a significant speed up in solving huge linear equations. And based on this, a bunch of use cases did appear already in the meantime. So the speed up allows us to solve intractable problems, for example, in machine learning. For example, in implementing support vector machines that are used for classification, right? There are also speed ups for clustering algorithm, feature extraction algorithm, and you can use these kind of algorithms to do fraud detection, build recommender system, do outlier detection. In optimization, for example, to solve combinatorial problems like the traveling salesman problems, minimum spanning tree, max cut, and so on, that you need to do scheduling, route planning, optimizing power grids. We use quantum computing in the area of simulation, like crash simulation or body stability by the means of solving huge linear equation systems. And there are tons of applications or envisioned applications in material science, drug discovery, and I try to sketch at the last 15 minutes of the presentation what can be done today, what is realistic today. That means for the next about 60 minutes, I will introduce the notion of a quantum bit and quantum registers, what are operators to manipulate these quantum bits, how do you program these quantum computers. As a sample, I give a little glimpse on factorization, and we will dive much deeper into the lecture that I'm starting next week at TU Vienna on this subject, together with Johanna Bartzen. Then I give an overview of what we call the NISQ area. This is the current era we are in of quantum computing, and then I give a brief conclusion before I'm sure that we are going to discuss a couple of these subjects. So what are quantum bits and quantum register? So a quantum bit, I abbreviate as qubit. Typically you write QU bit, but I'm lazy. So a quantum bit is in the two classical states, true or false, false or true at the same time. And in quantum physics, if you are in two states at the same time with a certain probability, you call it the superposition of the states. That means a quantum bit is a combination, a linear combination of false and true And these factors here are in fact complex numbers, right? Complex numbers where the sum of the squared moduli is equals to 1. That means it's a vector of length 1, right? And thus it's a vector on the unit circle, right? And 0 and 1 are considered to be the basis of the state vector, the base vectors. That means here you have the unit sphere, here you have 0, so 0 is this vector, 1, 0, and 1 is this vector, and this strange notation is called the Dirac notation, and these symbols are pronounced ket 0 and ket 1. These are the vectors, and the qubit is a point on this unit sphere. But alpha and beta are complex numbers. That means, in fact, this is a point in a four-dimensional space, a point of length 1. It's not in R2, it's in R4. That means C2, because these are complex numbers. That means this is a point on a three-dimensional unit sphere in a four-dimensional space. And this is hard to grasp, hard to understand. But we want to understand it in order to understand how to manipulate these qubits. And there is a very, very nice pictorial representation called the Bloch sphere. It's a physicist. And the Bloch sphere basically says you can represent any point on this three-dimensional space, on three-dimensional sphere in a four-dimensional space, as cosine theta over 2 ket 0 plus e to the power of I rho sine theta over 2 ket 1. That means you only need two angles, theta and rho, in order to determine the state of a qubit. And this basically means you can use it as coordinates on this two-dimensional sphere in three-dimensional space. You take the angle theta from the z-axis and the angle rho from the x-axis. And if you do so, you result in a point on this sphere. And this is a very important representation of a single qubit on the Bloch sphere. Having this representation, we can grasp an intuition of the power of a quantum bit. If you take a look at a classical bit, the bit is either 0 or the bit is either 1. That means there are two potential values. If you take a look at a quantum bit, well, the quantum bit is a point on this two-dimensional sphere. That means it's an arbitrary point on this two-dimensional sphere, although 0 is the north pole and 1 is the south pole. That means you have uncountably you have an infinite set of possible values of this qubit compared to two potential values. This gives a first intuition why these qubits are so powerful, because they have a lot of values that they represent that you can manipulate. So a quantum algorithm, as we will see, in fact, is manipulating the states of qubits or multiple qubits called the quantum register. But at the end, if the quantum algorithm stops, you need to measure the state of the quantum computer to get results out of the quantum computer that you can process classically, continue processing classically. This is called measurement. So classical bits can be read, but that means you can find out the exact state of a classical bit. If you measure it, you know it's 0 or 1. But if you measure this strange qubit, right, well, the qubit is a superposition, alpha ket 0 plus beta ket 1. So if you measure it, then you destroy the superposition. So any point on this unit sphere at time of the measurement must decide whether it is 1 or 0. And this alpha and beta, this coefficient, they basically determine the probability. So if you take a qubit X that has this superposition, you need to take the squared modulus of 0 to find out the probability that you will measure 0. And if you take the squared modulus of beta, this is the probability that you measure 1. So measurement is the mechanism of retrieve the result of an algorithm out of a quantum computer. You can read it, but if you read it, you destroy the superposition, because at this point in time, the qubit must, quote unquote, decide whether it is now 0 or 1. And that means a qubit can only be read once. Tough luck for database people, right? Databases in quantum are very hard to realize because you can read only once. And that means measurement is a random experiment. This is also of utmost importance. Quantum computers perform random experiments. You run the algorithm stops with the quantum state in the quantum computer, and then you must perform a measurement in order to get values out of it that represent the result. And values basically means you get a value based on this random experiment because you destroy the state in the quantum computer, and with a certain probability that is described by the state that the algorithm produced, you will get the result 0 or 1, or more combinations out of it. It will be seen in a second. So what is this algorithm that you perform before you measure? So what are, first of all, the single computation steps? Well, a computation step takes a state in a quantum computer, which is a unit length vector. It manipulates it and produces a new state, which is again a unit length vector. That means a computation step in a quantum computer turns a unit length vector into another unit length vector, and such a linear map is called a unitary map, or in real space, it's an orthogonal map. So single computation steps in the quantum computer are unitary maps. That means matrices. That means you manipulate qubits by applying matrices. This is the first fundamental difference. Algorithm consists out of sequences of unitary maps, right? So, and here's a very simple algorithm, this coin flipping that I mentioned briefly before. So you want an algorithm that produces 0 with probability 50% and 1 with probability 50%. That means you want an algorithm that produces true, real random numbers. We know that we can't do that in classical computing, but we can do that as I will show in the quantum computing. So you initialize the qubit in its so-called ground state. That means you initialize it with 0. Then you apply a matrix called the Hadamard matrix to the qubit, and then the qubit changes its state, and then you measure the qubit. And what this does is, and I will show you why this is the case, the algorithm produces a completely random bit, which is classically not possible, because classically you can only generate pseudo random numbers. But there are also algorithms that won't work at all. The most famous algorithm of this kind is called the no-cloning theorem. The no-cloning theorem says that there can't be any algorithm that copies an arbitrary quantum bit into another quantum bit. That means you cannot only, it is not only true that you can't read, that you can read a bit or a quantum bit only once, but even worse, you can't copy a quantum bit. This is the no cloning or no copy theorem. This is as an example of an algorithm that can't be done in quantum computing. So, and now a quantum register, this is a qubit, this is the Bloch sphere. A point on the Bloch sphere is a state of a single qubit. You can bundle qubits together in something what we call a quantum register, right? While a classical register is a series of n bits, a quantum register with n qubits is a superposition of 2 to the power of n states, because each of this qubit can be in the state 0. Then you have n zeros here, or one can be in state 1 and the others can be 0, and so on. So you have 2 to the power of n combinations of 0 and 1. And the quantum register as a single qubit is in superposition of 0 and 1. A quantum register is in superposition of this 2 to the power of n states at the same time. That basically means we will call this quantum parallelism, another fundamental thing that happens in quantum computing, because a classical register with n bits has a single value at a time, because the individual bits are binary representation of a single number. But the quantum register with n bits has 2 to the power of n values at the same time. And for example, if you have a quantum computer with 50 qubits, 50 qubits is 2 to the power of 50, which is 10 to the power of 15. That means you have peta information, right? At the same time, extremely powerful. And you can manipulate it if it's entangled. I will discuss entanglement as another important concept next. So you can manipulate these values in a single step. These number of values can be manipulated with a single step, quantum parallelism, which is another source of the incredible power that quantum computers basically have. So quantum computers can manipulate 2 to the power of n values at the same time, that we call quantum parallelism. So by now we understood what the content of a qubit is. An infinite number of potential values are there. We discussed superposition. That means you have enormous number of values at the same time with a certain probability. And then we have parallelism, that you can manipulate this huge number of values in single steps. And by the way, 50 qubits is what that was much 2 years ago, but IBM, for example, will deliver in May or June 127 qubits, a machine with 127 qubits. So this is something that is real. Yeah, you can use these kind of machines. Here you have a very, very small chip, a quantum chip. These are the qubits, and these are microwave caviators that, so to speak, transport microwaves to the qubits to manipulate them. You have connections between the qubits to manipulate 2 qubits at the same time, and so on. This is a little picture. Typically, you represent it as a graphics, right? And you abstract it to a graph. So the connections here, the edges of the graph, basically represent connections between the qubits, because they become important, because often you need to manipulate multiple qubits at the same time. And for this purpose, physically, you need connections between the qubits. So these graphs will appear to us a couple of times during the presentation. And here you see a real quantum computer that I had the pleasure to see. This is the quantum computer. What you see here is these wires are basically the caveats that transport the microwaves, right? And the real quantum computer is below here. So I zoom in here, and what you see here now, this is the chip that contains the individual qubits that you manipulate. And this looks ugly, right? But if you buy such a quantum computer, it looks really fantastic, right? This is here a Curiostat, because this is a superconducting computer that I've shown, and it runs at 0014 Kelvin, microkelvin. It is order of magnitude colder than the outer space, right? And this is a significant technical problem to cool down the superconducting chips to be able to have quantum bits here. So I said before, after an algorithm runs, you get the result in the quantum computer. For example, you result in this linear combination of the states of the quantum computer. These are the states of the quantum register. I said that the state is a superposition. That means a linear combination of these states. And if you measure it, you result in this state with a probability moduli alpha I squared. And in order to retrieve a result, you don't run the algorithm once, but you run it many different times. A single run is called a shot. So you run the algorithm. So the default in IBM Q is 1024, and you can go up to several thousand shots. And if you run the algorithm several times, you perform the measurement after each run, you get a probability distribution of the individual values that resulted after the run of a single iteration of the algorithm. And if you take a look at this probability distribution, right, the final result of the algorithm is the result with the highest probability. You take this one, right? This is the result of the run of a quantum computer. That means the more often you run, right, the more precise will the result basically get, something that I will also explain in the course of the talk. So the design goal of a quantum algorithm is to achieve a distribution that allows you to retrieve the result with the most highest probability. For example, the Grover algorithm that does the unstructured search produces a distribution such that the search result appears here with a very high probability. Other algorithms try to achieve a distribution where the majority of results have a high probability, right? So this is the art of a design of a quantum algorithm to understand how to produce a quantum state that shows one of these two probability distribution. Either the single result is distinguished in this distribution, or you result a distribution where the majority has certain values, and then you can infer something from it. Right? This is done by the Dot-Joshua algorithm, for example. This is done by the Grove algorithm. And those who are going to attend the quantum computing lecture on Monday will discuss these kind of algorithms. So here you see a quantum register. It has 2 qubits, right? And it's a uniform superposition of the qubit 00, 01, 10, 11. And what you can see is you can write this register as a product. It's a tensor product, so a special kind of product, but we can ignore it for the sake of this presentation. It is the left qubit multiplied by the right qubit, and if you apply the law of distributivity, you get this register out of it. This state of a quantum computer is called a separable state. Separable because you can split the quantum register into a product of the states of its individual qubits. So what that means is, here's another separable state. If I measure this state, here the first qubit, I will get with 100% probability the state 0, because if I measure it, I get the 0, and then it collapses either to this state, or it collapses, if I happen to measure this qubit, to this state. So if I measure, right, so if I measure a 0, what remains is this state, and I have still 50% chances to measure a 0 on the second qubit, and a 0 on the second qubit, or 1 on this qubit. So everything is fine. If I measure, the state is destroyed, and the remaining state still has all the probabilities to be in 0 or 1. And this happens because this is also a separable state, because this state is the product of the left qubit times this state of a product of the right qubit. Here's now another very strange state. Not a strange state. In fact, it turns out that these states are most often in quantum computers. So this state, if you measure here the first state, if you measure a 0, then this state is gone, right? Because the first state was 0, here is a 1, this is gone. So you measure the first bit 0, then you know that the second bit is a 0 too. Or if you measure the first bit as a 1, then you know immediately that the second bit is in state 1 too. That means measurement of one qubit immediately determines the state of the other qubit. And what you can show is, in experiments, you can move the 2 qubits even far apart. And if you measure at location A the qubit, you immediately know what the status of the qubit in state A is. This was shocking to Albert Einstein, and this is now called the Einstein-Podolsky-Rosen paradox, or the EPR paradox, right? That measurement of one part of a physical system immediately determines the part of another system, and even if they are far apart. So it sounds to conflict with general relativity. In fact, it doesn't, right? But this is very strange to understand, very hard to understand. We need to accept it, that nature is this way. And this state is not separable. You can't write this state as the product of the two encompassed qubits. This is why we call it entangled. Auf Deutsch verschränkt, entangled. So entanglement is another very important concept in quantum computing. And here's now an envision of what entanglement means. So these are the 2 qubits, the 2 particles, right? They are close together. You entangle them, and then you basically bring the 2 dices to different locations. This remains on Earth, and this is what you fly to the moon. Then on Earth, you decide to toss or to roll the dice. So you roll it, and once the result is known, you immediately know what the dice on moon is. That means immediately the states are there, because the states are entangled. And entanglement basically means the following. If I have a state of a quantum register that is not entangled, I can manipulate here this blue qubit, and the other qubits are absolutely unimpressed. But if I create an entangled state and I manipulate one qubit, all the other qubits are manipulated too. So this is the power of entanglement, right? You can manipulate the high dimension, the high number of values if they are entangled in a single step. And entanglement is unique for quantum computing. You can't simulate it on a classical computer, right? This is the real important. Superposition can be simulated if you have a low number of qubits, up to 40, 45 qubits can be simulated on high performance computers, but 50 already is very hard to simulate. You can't simulate entanglement. And every computation on a quantum computer that is not involving entangled qubits can be performed with the same efficiently with classical computations if you only have a small number of qubits. And you can even prove that every quantum algorithm that shows exponential speedup compared to classical algorithms must exploit entanglement. So entanglement is of utmost importance in quantum computing. And if you take a look at algorithms, the first thing that they do is they create superposition. And then after a few steps, they create entanglement. And then the magic of quantum computing often happens. Here's an example what you can do with entanglement. It's not really an algorithm, but the so-called protocol. We assume that at location A, Alice, at location B, Bob, that at location A, you have a qubit psi A prepared, and you want to transmit classical information from Alice's location to Bob's location, so that Bob can, based on this classical information, can reconstruct the qubit. Imagine that classical information, each bit has only 2 possible values. So you want to commit only a small number of values to construct a qubit that potentially has an infinite number of potential values. This is called quantum teleportation. This can be done, and it can be done based on the following assumption. Alice and Bob must agree in advance on an entangled state of 2 qubits. That means of 2 dices. They are entangled. Alice remains 1 dice at her location, and Bob takes his dice, his quantum bit of the entangled state with him. Right? And then you only need to exchange 2 classical bits from Alice to Bob, and Bob can reconstruct any quantum state that Alice prepared at her location. That means here's Alice, here's Bob. Both have an entangled qubit. So Alice has a single qubit, Bob has a single qubit of an entangled 2-qubit state. What Alice does is Alice prepares a completely new, unknown to Bob quantum state, and then she transports 2 classical bits to Bob. And as soon as Bob receives these 2 classical bits, Bob can reconstruct the quantum state at his location. Please note that the location at Alice's side, that the quantum bit at Alice's side did disappear. It must disappear because based on the no cloning theorem, you can't copy a qubit. That means if Bob reconstructs it here, the state here is gone. So the magic here again is entanglement. It was a simple example. It's not simple, but it was a very nice animated example of the power of entanglement here. And again, at location A, you manipulate the entangled state, then you perform a measurement, and the result of the measurement gives you the 2 bits information that you send over to Bob, and Bob, these 2 bits encode, so to speak, the name of an algorithm that Bob needs to run in order to materialize the qubit that Alice had before, right? So this is the magic, but the magic is entanglement. Without entanglement, you can't do it. So how do you now manipulate quantum registers? First of all, how do you manipulate individual qubits? Well, for this purpose, I said before, the manipulation of a qubit is done by unitary maps. This is the symbol of a 2-dimensional complex vector space that represents a single qubit. We call it a 1-qubit operator or a gate. And there are 3 very famous gates, the so-called Pauli gates or Pauli matrices by Linus Pauling. Here you have the Hadamard gate that is important. The phase matrix is important. The pi/8 matrix is important. These are very important manipulations of a single qubit. And this is pictorial representation. What you see is the lines represent the individual qubits, and the squares and their names represent the matrices that are applied. And the control flow, the time travels from left to the right. So here you have a state of the qubit. Now H is applied, and then the result of the qubit is fed on to further gates. So here's an example. X was this matrix. I can go back. X is the matrix 0, 1, 1, 0. And if I apply X to ket 0, the quantum fault state, the quantum fault state is 1, 1, 0. As I mentioned a couple of minutes ago, this is the X matrix. If you multiply it, you get the vector 0, 1, and vector 0, 1 was exactly the ket 1 state, as I discussed when I discussed that the qubit is a unit length vector. And if I use X on ket 1, I get ket 0. That means the Pauli X matrix is what we call in classical computing the negation. If I apply the Hadamard matrix to the state 0, this is the Hadamard matrix, right? This is the state 0 as a vector. If I multiply it, you have 1 times 1 plus 1 times 0 is 1. You have 1 times 1 plus minus 1, 0 is 1. This is this vector. I can split this vector 1, 1 in 1, 0 plus 0, 1. 1, 0, but again is ket 0. 0, 1 again is ket 1. And this is a state in superposition. That means the Hadamard gate is used to create superposition. You initialize the quantum computer at the beginning of your algorithm to its ground state, 0. Then you apply Hadamard to create a uniform superposition in your quantum computer. And then you apply more magic that I'm going to explain next. The Pauli operators have a very nice geometric interpretation. What the Pauli operator does is, in fact, it's the exponential of a Pauli operator. We will discuss it in the lecture, what that basically means. So the Pauli operator, the Pauli X, basically takes a qubit on a Bloch sphere and rotates it around a certain angle theta around the x-axis. The Pauli Y operator is the rotation around the y-axis, and the Pauli Z operator encodes rotations around the x-axis. Right, so you can rotate around x, around y, and theta, and you can, of course, determine the angle theta here. This is a very nice interpretation again. What happens? I skipped over this. So the rotation x negates, it turns 0 into 1, and this is in fact a rotation around the x-axis by the angle pi, by 180 degrees, and so on, and so on, and so on. So the question but now is, can we find universal sets of qubit operators? And I call a set universal if every other qubit operator is a finite combination of the operators of U, and U should be as small as possible, because these operators are the operators that the hardware providers must implement in order to compute, to realize any other one qubit operator. Right? And it turns out, if U is an arbitrary one qubit operator, you can represent this one qubit operator by 3 rotations. You can rotate first around the z-axis, then around the y-axis, and next finally around the z-axis. And this is some global phase here. And this is what we will also prove in the lecture and use examples how to compute this rotation representation of an arbitrary operator. So that means every one qubit operator is a composition of 3 rotations on the Bloch sphere. And these rotations are in fact the exponential of Pauli Z and Pauli Y. That means the Pauli operators are universal for each and every one qubit operator, right? 3 matrices must be implemented by the hardware provider in order to be able to perform any unitary transformation of a single qubit. This is nice. Now let's take a look at quantum registers. If I have a quantum register consisting out of n qubits, this is the n times tensor product, then a unitary map in this high-dimensional space is called an n-qubit operator, or quantum register operator, or a quantum gate. And again, we are looking for hopefully a very small set of universal quantum register operators, so that every quantum register operator is a finite combination of operators from this hopefully small set of operators U. In order to show that something exists, I need to introduce one of the most important two-qubit operator, the so-called controlled NOT operator. And the controlled NOT operator says, if the first bit qubit is 1, then the state of y of the second qubit will be negated. And this in mathematics means this is the addition modulo 2, right? If x is 0, y remains intact. You don't do anything with y. This is a controlled NOT, controlled by the status of x. Right? This is a unitary operation. It's very simple to prove because the matrix is a permutation matrix, and any permutation matrix is a unitary matrix. And this is the pictorial representation of the gate. It says x is the control bit. The solid circle means if x is 1, then the qubit y will be negated. And this is the plus sign with the circle that is shown here. So if x is 1, y will be negated. If x is 0, y will not be affected at all. This is a unitary map. And now, if you take this separable state, this state is separable because it is the product of the first qubit and the second qubit state. If you apply C0, well, C0 is a linear map. You can move 1 divided by square root 2 to the outside. Then you have C0 applied to 0, 1, and C0 applied to 1, 0. Here, the control bit is 0. That means the second bit remain intact. Here, the control bit is 1. That means the second qubit will be negated, 0, 1, 1, 1 results. And this is an entangled state. So while Hadamard, the Hadamard matrix is used to prepare superposition, the C0 is the workhorse in quantum computing to produce entangled state. So it is of utmost importance because entanglement is the workhorse in quantum computing, right? Here's where the magic happens. But C0 does more. If you apply C0 to this entangled state, right, then the control bit is 0. It remains intact. The control bit is 1. Here you produce a 0. This state results. And this is the separable state here. That means C0 can not only transform separable state into entangled state, but you can unentangle a state by taking an entangled state, apply C0, and then you get a separable state. And C0 is important to realize any quantum register gate, because you can prove that the set of 1 qubit operators, that means the Pauli gates, and C0 is universal. That means a quantum hardware provider must implement the exponentials of the Pauli matrices plus the C0 gate and can compose any operation on a quantum register out of it, right? But if you want to have a gate that manipulates n qubits, you need exponentially many 1 qubit operator and C0s to rewrite or to produce this any n qubit quantum operator. And this is by far not acceptable, right? Because if you have 50 or 100 qubit, right, you need 4 to the power of 100 times 100 square operators in order to realize an arbitrary 100 qubit operation. This is absolutely not efficient. Tough luck. So 1 qubit operators can be easily realized, but n qubit operators can't. What to do? Well, we can approximate an arbitrary unitary operations on n qubit with arbitrary precision. And in order to do so, you need again the famous C0. You always need it because this is needed for entanglement. And then you don't need the 3 Pauli matrices, but the matrices that are shown below the Pauli matrices on the corresponding slide. You need Hadamard, you need S and T, and then you can approximate them with arbitrary precision. What does approximation mean? Well, if you recall, an arbitrary algorithm, which is a series of unitary transformation, but a composition of unitary transformation is again a unitary transformation. This is why you often represent an algorithm only by a unitary transformation. This produces a probability distribution of the results. Approximation means you take an epsilon tube around the true distribution, and approximation means you find the composition of HST and C0 that remains in this epsilon tube in order to approximate as close as possible the real result of the quantum algorithm. That means the statistics of measurement don't differ. And the measurement is what produces the results. That means you measure the distribution, and the value with the highest probability is the distribution. And if you take epsilon very, very small, this orange distribution will be very close to the maximum of the blue distribution, right? And the length of the sequence that you need in order to approximate U based on HSTC0 operations is logarithmic, polylogarithmic in 1 divided by epsilon. And this is absolutely acceptable. This is how quantum computers work, right? They emulate, they rewrite a universal unitary matrix based on these 4 other operators, create them the composition, then the algorithm is basically run, and then you measure and get the result. So, but for this purpose, in order to make that really happen, what you need is a special kind of algorithm. The complexity class is called BQP. So a problem is called bounded error quantum polynomial time algorithm. If it can be solved on a quantum computer with error probability less than 1/2 minus epsilon. So this epsilon is important. You not only solve it with 50% probability, but the solution is produced with higher than 50% probability. This is a BQP algorithm. And BQP is for quantum computing what P is for classical computing. That means if you have an algorithm that is BQP as a quantum computer scientist, you are absolutely proud, because then you have a workhorse that can be used very efficiently on a quantum computer. And how do you use it? Well, if A is the BQP algorithm, then you run the BQP algorithm many times, n times, and the result with the highest frequency will be the output, the true result. How does that work? You can prove that success amplification works. So for example, if omega is the maximum probability that you tolerate to accept the wrong result, then we will prove in the lecture, so it's easy to prove, that after this number of iterations, so epsilon is this epsilon that is the epsilon from the algorithm, the BQP class, right? And this omega is the probability you are going to tolerate errors, right? And then if you iterate this algorithm n times, the result is correct with this probability. So the example, if you have an algorithm with epsilon 1/4, you are willing to accept an error with 1/1000th probability, then you only need 56 iterations of this algorithm to get the correct result with 99.99 probability. This is what we call success amplification. So now we discussed what these operators are, how you can, any unitary map can be represented or approximated by a universal set of only 4 operators. Now, how do you program these beasts? So what you see here is, and we will do that also in the lab in course of the lecture, this is the tool that IBM offers in the internet. Everybody can get a user ID and basically play with the quantum computers that IBM put online. This is called the circuit composer. The circuit composer, this is here a line, we call this a chord, and the lines represent the qubits. And then again, remember the algorithm flows from left to right, right? So what you do then here is, here you see the gates that you have available. You basically take the X gate and drop it, drag it here to the qubit 0. This is the X. And this gate basically means I measure it. So it's not a gate. It indicates that it's a measurement operation. And if you take this and execute it on a simulator, the simulator returns the correct result. Here's the 1, here's the 0. X negates the 0 to 1. And if I measure then the ket1 state, I result with 100% probability in a 1. So, and here's what the simulator basically does. And remember, the simulator does linear algebra, so it produces always exact result if you have only a few qubits. But if I execute it on a quantum computer, on the real QPU, quantum processing unit, what you see here is, in this example, I produced 94% probability, I resulted with 1, and 6% I resulted in a 0. And this is okay, because the result is the result with the highest probability. That means my quantum processor produced, as a result of the algorithm, a 1. What you see here is you not only have a graphical editor to write your quantum programs, but there's also a language behind it that is called a quantum assembler, because this is an open language. It's called OpenQASM. In the meantime, we have OpenQASM 3.0 proposed, right? But many people still support OpenQASM 2.0. What you see here is you have a quantum register, and here I allocate 5 qubits. I allocated CREC, means classical register. I applied the X matrix to the qubit 0, and then I measure qubit 0, and the result should be stored in a classical register 0. So this is a very simple language, this quantum assembler. Here I create superposition. Remember that out of 0, by applying the Hadamard matrix, I created the status in superposition. So if I measure it, I expect that in 50% of all cases, right, because the modulus squared is 1/2, right? In 50% of all cases, I expect to measure 0. In 50% cases, I expect to measure 1. And in fact, it happens nearly, right? It's a random experiment. The more experiments I run, the more equal will the probabilities be. Here I used 1,024 shots. So this is roughly a status in superposition. Here I create entanglement. Remember, entanglement is created. I apply a Hadamard, I create superposition on the first qubit. Then I apply, then I entangle the first qubit with the second qubit. And this is how you read it. You apply H to the first qubit and you do nothing with the second qubit. I apply H to the first qubit. I do nothing on the second qubit. This is the identity matrix. And here is the tensor product of the two matrices. And after that, I apply C0. So this is the matrix multiplication. C0 matrix is multiplied by the tensor product of the H matrix and the identity matrix. So H applied to the first qubit 0 results in superposition of the first qubit. The second qubit remains intact. That means this is this part. And now I apply C0. So then I multiply it out. I get this status here. Then I apply C0. And then I get the entangled state that we saw a couple of times before. And in fact, if I execute on a real quantum computer, I measure the two qubits, and in 50%, I get 0, 0. And in the other 50%, nearly 50%, I get 1, 1. So this is how we generate superposition in entanglement on a quantum computer. Of course, you don't, I personally program in quantum assembler. I'm old, much older than most of you are. But most quantum computer providers support Python libraries in order to manipulate the quantum computers. They are, so to speak, a shell on top of the quantum assembler. So you can use Python, which is a Python sugar on top of the assembler if you don't want to program this in assembler. Now here I give you a glimpse of what a quantum algorithm look like that solves a real problem, namely factorization. So here is Don't Be Shocked, Shor's algorithm. I don't dive into the details. You see a lot of classical stuff, especially mainly you need to compute the greatest common denominator of two numbers. N is the number that you want to factorize. And what we try here is we choose an arbitrary number between 1 and n, a, and then we need to find out what the period of this number theoretic function is, a to the power of x modulo n. This is a periodic function, as you can easily see if you make a value table. And if you know the period of this function, you can compute a prime factor of this number, right? But the magic is you need to be able to determine the period, and this is classically there are only exponential algorithms known, right? So if you know the period, you find a proper divisor within k runs with a probability 1 greater than 1 minus 1 divided by the 2 to the power of k. And the overall runtime of this algorithm is polylogarithmic, which is an exponential speed up compared to the best known classical algorithm. And so the heart is you do a lot of classical stuff on a classical computer. And what you do is you determine the period based on a quantum algorithm. And for this purpose, we need to understand how to approximate periodic functions. So every piecewise continuous differentiable function can be periodically extended, thus approximated by its Fourier series. So here you have an arbitrary piecewise differentiable function. You extend it over the real line, and then you can approximate it by a Fourier series. So a Fourier series basically is the following. We have sine x 1/3 or sine 3x and so on. And if you add these graphs up, you get exactly this approximation of the first order of the first parts of the Fourier series, right? The Fourier series looks like this, and the more pieces you take to the Fourier series, the more precise you get the original function. And what is interesting here is this is the Fourier series, and what I do is I take the individual trigonometric functions here that make up the Fourier series, and then I see I have sine x and the amplitude is 1, sine 3x, the amplitude is 1/3, and so on. So I basically take the spectrum of this function and take a look at the atomic trigonometric functions, and then I project the frequencies. I project to the frequencies, and I'm only interested in the amplitudes of the frequency. So sine 2x doesn't appear, so the amplitude is 0. Sine 4x doesn't appear, the amplitude is 0. But sine 3x appears, and the amplitude is 1/3. So I take this one. So these numbers are basically equivalent to the Fourier series. You only need to know these numbers in order to understand what the Fourier series is, and this is called the spectrum. And the computation of the spectrum of an arbitrary periodic number is called Fourier transformation, right? And this is what can be done efficiently on a quantum computer. Here, what you see here is a matrix. These omegas have nothing to do with the probability that does success amplification. These are the complex units, unit roots, right? You don't need to understand it here. We will discuss that during the lecture at length. But what we do here is we have discrete values of a function, this a to the power of x modulo n, and then you apply this matrix, and then you get out the spectrum. That means Fourier transformation becomes matrix multiplication, right? Somehow you materialize discrete values of this function a to the power of x modulo n. You apply this thing, and then you get the spectrum out of it, and based off this, you can compute the period. Well, this is the algorithm in a nutshell. Not really, you shouldn't understand the details, but only the underlying mechanics. What we will do is we will compute this function based on a unitary operator, UF. You turn this function to a unitary operator, and this then basically produces the function table. Each x will be paired with its function value fx. In the first half of the quantum register, you have x. In the second half of the quantum register, you have f of x. They are here, their status is entangled. That means I will then measure in the algorithm, Shor algorithm, the second part of the quantum register f of x. That means I will result in f of x star for a random x star. And then the rest, the first half of the quantum register, will remain in a status that is the superposition of all the arguments that are mapped to f of x star. And then I analyze what remains in the first half of the register based on Fourier transformation. And this is some stuff that we are going to discuss. And then the period will result. As I said before, this is polylogarithmic. That means the Shor algorithm shows this kind of behavior, while the best known classical algorithm shows this exponential behavior. And more concrete, what that means is, if you want to crack an RSA 2048 key, the key has been defined and standardized in such a manner that the best known classical algorithm needs the lifetime of the universe to crack the key, which is pretty safe. But if you have a quantum computer with enough qubits, I will discuss what enough means. Error-corrected qubit, this is very important. Today's qubits are error-prone. Here we assume error-corrected qubits. Then a quantum processor with 1 gigahertz solves it in about a minute. Today's quantum computer already have 5 gigahertz or more. That means you can solve it much faster, right? So if we have error-corrected qubits, a few thousand error-corrected qubits, then you can crack any key in about a minute, which is a real threat to our security infrastructure. How many error-corrected qubits you need? Well, 2 to the 2048 times 2, that means 4,200 qubits are needed to crack RSA, but you need a couple of millions of operations, but these are error-corrected qubits. What IBM and Google tell us in their roadmap is that by the end of this decade, they will have 1 million error-prone qubits. And well, there are mechanisms, for example, where you need 1,000 error-prone qubits to realize a single error-corrected qubits. That means if you take this, then you come in the era of some 1,000 error-corrected qubits. That means you can crack RSA 2048 within 10 years or a bit more. And this is a real threat. But it can't be done today, because today we are in the so-called NISQ era. So in order to explain what that means is, we need to take a look how a quantum algorithm looks like. A quantum algorithm, here called a quantum circuit, consists out of different gates. You need 1 qubit gates and 2 qubit gates, C0 effectively, in order to build an algorithm that manipulates a quantum register. And what you can do is you arrange the gates that can be executed in parallel in layers, and the number of layers you need in order to perform the algorithm is called the depth of the algorithm, while the number of qubits that are manipulated is called the width of the algorithm. Here's an abstract example. The algorithm in this virtual paper says, first apply this qubit and this operation, then you apply this operation parallel with this, and finally you apply this operation. Well, what you can see here is this gate is independent of this gate because it manipulates very different qubits. So I can move this gate over to here. The same is true for this gate and for this gate. Then this layer is empty, and finally I can move this gate into the second layer. That means that the depth of this theoretical algorithm, in fact, is 2, and the width is 7 because it manipulates all the qubits. In this example, I can move S in parallel to H. I can move this H to be performed in parallel to H and S. I can move the C0 closer there. I can move this C0 closer to there, and this T can be executed in parallel to this C0. That means this algorithm that you may have read in a paper is in fact an algorithm of depth 3 and of width 3 because it manipulates this qubit and this qubit and this qubit, and the other qubits are not needed at all. So this is a first glimpse. You need some sort of optimization. You need to take a look at circuits and you need to optimize it. And this is a very simple, a trivial kind of optimization. But the depth and the width of an algorithm are two very important characteristics. Because, first of all, an individual qubit is unstable by nature. So the status of a qubit may be inverted. It may be, so a qubit may be collapse to its diagonal state, which is called the relaxation time. So it relaxes within a certain time, the T1 time, from one state to its orthogonal state. Or it may jitter around its state, which is called the dephasing time. So it's not collapsing to its orthogonal, to its diametral state, but it's only change a little bit of the amplitudes, right? It's a random change of its phase, sorry. This is decoherence of a qubit. Qubits today are not stable. Here's an example of IBM-Q, just to give you an impression. These are three different machines. They have more online, right? Here, if you take a look here, so the current T1 and T2 times are about 100 microseconds. It sounds to be small, but it's already large enough to perform something realistically. So that means qubits may decay based on decoherence, relaxation, and so on. So what about applying classical error correction? Error correction requires that you take a copy of the bits, have a redundant bundle of bits, and then you observe whether some of them have been changed. But what works in classic doesn't work in quantum because you can't copy bits. That means the no cloning theorem already says, well, these kind of algorithms to provide error correction can't be done. Even worse, in classic computing, bits flip from 0 to 1 or from 1 to 0, but errors in quantum are continuous errors, right? You change the phase of a qubit only a little bit, but you have a continuum of errors that may happen to a qubit. So this kind of algorithms that we know from classical computing can't be applied. Right? I can't read a bit and use the information to correct it because reading will destroy the state of a qubit, so you can't apply it. And so qubits, you can't apply classical mechanisms in error correction, and even worse, the gates that you apply are inherent imprecise. Here's some intuition. Gates, the rotation, if you want to manipulate the qubit, right, you need to represent it as a series of rotations, but an individual rotation is imprecise because if you want to rotate around pi divided by a square root of 2, this is a not rational number. It's very difficult to rotate around exactly this angle. That means rotations are inherently imprecise. That means especially this composition of the three rotations that represent a unitary operator of a qubit has always a small error. Here are the error numbers. There's a C naught, has an error rate of 1%. And here you have 1 divided by 1,000. These are the error rates of C naught, for example. That means all algorithms that we implement today without error correction are noisy. We call it noisy because the individual gates suffer from errors and the individual quantum states, the qubits, suffer from errors. Now we come back to what is that the size of the algorithm in terms of the width, the number of qubits manipulated, and the depth, or the number of errors that are manipulated, that are the number of gates that are executed in parallel. This must be, W times D must be significantly less than the error rate of the machine. And I don't discuss how to measure the error rate here. That means if you want to manipulate, if you want to run algorithms that have many steps in parallel, in sequence, right? If D is large, W must be small. That means you can only manipulate a small number of qubits. But manipulating a small number of qubits can be simulated classically. So simulation of 40, 44, 45 qubits is, although you need a huge GPU cluster to do that, possible. But then you can't prove the advantage of quantum algorithm, of quantum computers. That basically means we want to focus on shallow quantum algorithms. Shallow quantum algorithms has only a few parallel layers, but a large number of qubits that will be manipulated. And you can't simulate large number of qubits. That means here we have the potential for quantum advantage, shallow algorithms, right? And this is the domain for the current machines, the NISQ machines, the noisy intermediate scale quantum computing. And how do we do this? Well, the secret here is hybrid quantum classical algorithms. So many algorithms consist out of a quantum part and the classical part. Even the algorithm that I've shown you before, the Shor algorithm, uses quantum Fourier transformation on a QPU and then needs some classical post-processing, right? Forget that I didn't discuss that we need continuous fractions, but we need some classical post-processing in order to crack a key. We call these kind of algorithms hybrid quantum classical algorithms. You have a quantum part, you have you measure the result of the quantum state that you produced, then you have some classical part, and then you iterate a couple of times. And the fact is that most quantum algorithms are hybrid. If you take a look at the paper, the papers present you the algorithm and say, this is the unitary transformation that you need to apply to solve problem X. And then the papers have in their fine print, they state, and for this purpose, I need at the beginning the following state prepared. And this state preparation is something that is out of the scope of many theoretical papers. That means what you need is, you need to have a classical pre-processing in order to generate a circuit that prepares the state that the algorithm does assume. And once the algorithm is done, right, you perform a measurement. And if you measure something, you get a probability distribution. And this probability distribution is also imprecise. I didn't discuss, but we will discuss in the lecture, that measurement takes a long time. And measurement is also very error prone. And then you need techniques to correct the measured distribution to be closer to the true distribution that the unitary transformation did produce. That basically means most algorithms today require classical pre and post-processing and iterations there on. This happens in the QPU. This happens in the CPU, in the classical environment. And most of these hybrid algorithms are variational in the following sense. The circuits that you apply in order to create a state in a QPU that is then measured is a parameterized circuit. You have parameters P1 to Pk. You perform a measurement, and then the measurement results in the measurement then is taken to produce a cost function, and this cost function is about to be optimized based on the parameters. That means you compute new parameters, take these parameters, run the modified circuit here based on the parameters, and then you iterate this loop. This is a variational algorithm or variational quantum algorithm because you vary the circuit that prepares the state in the QPU that you optimize in the CPU, right? This is a variational algorithm, and most of the workhorses that we use today in quantum computing are variational algorithms. So the goal of this variational quantum algorithms is that the circuit that is used to prepare the status has execution time TU that is clearly beyond the decoherence time TD of the QPU, right? And then the measurement, after the state has been prepared, you need to measure the measurement time. The time you need to measure the state should in addition be smaller than the remaining time from the decoherence time. That means your variational algorithm that is successful today in quantum computing must have an execution time plus a measurement time that is significantly less than the decoherence time. Remember, the decoherence time was about 100 microseconds. And these are today's workhorses that work on today's machines. I only mentioned here two important variational quantum eigensolvers. One is called VQE, variational quantum eigensolver, that approximates all eigenvalues of linear transformation of linear maps. There's an exponential speedup compared to classical algorithms. And the other workhorse is called QAOA, quantum approximate optimization algorithm. This is used in many algorithms that are underlying combinatorial optimization problems, QAOAs, right? And there are many algorithms like max-cut and so on that can be solved based on QAOAs. Once you accept that you have hybrid algorithms, then you realize that you need much more classical computing. So here's an example that we run at my institute. It's a machine learning. This is machine learning, right? You retrieve some data, right? Then you compute something. You map the data that you retrieved into some dimension, into some high dimensional vector spaces. Then you want to reduce the dimension based on principal component analysis, which requires eigenvalues. And here in this workflow, you have this algorithm VQE that I mentioned before, variational quantum eigensolver, that computes the eigenvalues of the covariance matrix in order to perform principal component analysis. Then the result is used to prepare a special kind of graph, right? And then you perform QAOA, this optimization algorithm, and solve and approximate the solution of max-cut, which then basically corresponds to a cluster, because here we want to perform some clustering. So what you need is, if you use a quantum computer, right, you need a lot of classical stuff. The classical steps are indicated by these hammers here, and the quantum steps are indicated by these atoms here, and these are in fact sub-processes indicated by the gears. So you need workflows. You need to have a bunch of classical code and quantum code, quantum assembler, for example, to solve a problem in the context of a quantum machine. And these artifacts, the classical programs and the quantum programs, they are dependent on this other, because this program, for example, may be a Python program that runs in Anaconda, that runs in Linux, that needs a VM, and so on. So what you need to do is you need to describe the artifacts that you need in order to run this workflow. And this is what is called in cloud computing a topology. So you need to describe the topology of your overall solution of your quantum algorithm. And then you need an infrastructure that executes the workflow. And if a certain workflow needs a classical program, you need to set up the environment of the classical program. If a set needs a quantum program, you need to set up, based on the model topology, this quantum environment. And then you need two orchestrations, so to speak, in lockstep, I say a superposition, in order to solve this. So at the sudden, a lot of classical technology, workflow technology, deployment technology that we know from classical middleware and cloud computing is desperately needed in order to solve real-world problems in quantum computing. And this is what we do in our project that we have, Planck. Planck is a lighthouse project of the German government. We have nearly 40 million funding to build such kind of an environment, because in practice you really need that. So to conclude, I'm a little bit over 10 minutes. Summary is, today's classical computer technology is reaching its limits, and quantum technology is needed to increase processing capabilities. Many quantum algorithms provide exponential speedup. I only give you one example compared with the known classical algorithms. Quantum algorithms are very different from classical algorithms because all you do is linear algebra. So that means very different skills are needed to solve the problems with quantum computer. Hardware of quantum computers are rapidly evolving. That means in the next few years, 5 to 10 years, you will be able to solve deep problems. In fact, you can solve problems today in simulation already. And most quantum applications will be hybrid, not only today, but also in future. Combination of quantum parts and classical parts. And here only I give one problems that we computer scientists can work on. For example, there is a proper engineering approach missing to build these kind of hybrid quantum applications. But even if you have pure quantum application, we need desperately a software engineering discipline to make that happen. I'll give you one example. one of my quantum computing specialists, a physicist, if I ask him, well, what about testing? You have your algorithm, developed a new algorithm, how do you test it? And the answer that was meant seriously, because I double-checked, is I'm a physicist, I don't make errors, right? But we computer scientists know that errors happen, especially in this environment. But I finished this talk with a quote of Enrico Fermi. So if you didn't know quantum computing before, right, then my hope is that you are still confused, but at a higher level. So that I managed to give you an impression in quantum computing. And now with the delay of 10 minutes, I hope that we have a bunch of questions.
In replacement of all the other 240, you know, it would not even be possible in times of COVID to have all the people in all the lecture halls at the TU Wien who were now kind of your virtual participants, yeah, due to the you know, restrictions of people in one room. It was very interesting, Frank, knowing you from the workflow area. You really managed to introduce workflow in quantum computing. This was very
sure.
So there are now a lot of questions in the chat, and it will be Martin Wagner who is kind of reading the question, posing it to you, and yeah, it would be great if you can answer them.
I do my best.
That was the plan.
Okay, so let's start with the first question, which was asked by Andreas Steininger. He asks, no, I'm so sorry, wrong line. It is a question from Niven Tanzer, who asks, what prerequisites do you need to start learning the mathematics for quantum computing?
What you need is you need to understand, in a nutshell, Hilbert spaces. That means complex vector spaces with the scalar product that are, okay. And then you need to understand eigenvalues, eigenvalues, eigenvalues. You need to understand tensor product that is often not taught in math classes. And this is what we are going to teach in the first couple of hours in the quantum computing lecture.
Okay, thank you. Another question by Christoph Bogner. In the general public, especially the cryptocurrency community, there's general fear and dread on the topic of quantum computing. You already shortly brushed the issue in your talk. As an expert on the topic, what is your personal opinion on this?
That the fear is rightful. Right. So if we have powerful quantum computers with a couple of thousand error-corrected qubits, and again, as I said before, if you take a look at IBM and Google, they will have 1 million error-prone qubits, right? If you divide by 1,000, some divide by 5,000, right? The number of qubits to crack RSA, right, comes close. It will take a couple of years, but then you can crack keys. But this is not only a danger in future. If you consider that companies have confidential information, confidential data that are stored, and they must kept and stored for decades, right? If you produce cars, you must store the construction details of the car for decades, because if a crash happens, right, then somebody sues you, you need to prove that this is not your fault. These kind of confidential data are already out there. Right, and they can be cracked in a couple of years if Shor's algorithm is implemented correctly. That means we need to prepare ourselves to change the security mechanisms that we have implemented in today's software. Many of you are too young that they remember the year 2000 problem. The year 2000 problem meant that you needed to change software that only stored dates with 2 digits. 95 meant 1995 and not 2095. You need to change tons of software. It took many years to change it. A lot of money got burned to change it. And we need to do the same with several orders of magnitudes more to change all the security stuff we have in our software, right? What is currently done is the NIST, the National Institute of Standards in the US, they are standardizing, if I'm correct, 2021, 22 algorithms from the post-quantum cryptography area. Post-quantum cryptography doesn't mean once quantum is gone, but it means if we have powerful quantum computers, what kind of encryption mechanism do we have available that are not yet cracked by a quantum computer and that are not yet cracked classically? So, and they have this many quantum algorithms because you can't prove that the algorithms that they are standardizing can't be cracked, but they say they can't be cracked today. And in order to be foolproof, they standardize 20 plus algorithms. And the infrastructure that we need to build is called an agile encryption infrastructure. Agile encryption basically means that you randomly pick an algorithm to encrypt something in your infrastructure. It will be plug-in based so that you can basically exchange algorithms that are basically correct. It's a huge endeavor that we do. The other alternative is we fall back to symmetric keys. Symmetric key encryption. Symmetric key encryption can be done based on quantum computing. You can prove that there are algorithms, BB84 algorithms, how you can exchange symmetric keys, but there we need so-called quantum channels. Right? So the copper cable or WLAN doesn't work anymore. You need laser connections between 2 points or fiber channels between 2 points in order to exchange quantum information, to exchange symmetric keys. Another significant investment that we need in order to protect ourselves in the not too far future. This was a lengthy answer for a short question.
Thank you. There is another question from a colleague from University of Vienna, Peter Reichel, who would like to know if quantum algorithms in the field of machine learning are mainly based on VQEs or if there are also other approaches.
VQE and QAOA. We are also playing around with Boltzmann machines for clustering, which are neither VQE nor QAOA. So there are a couple of algorithms that are used in this area.
Thank you. Then Andreas Krieger would like to know what are error-corrected qubits and how do we get them? Are you referring to the relaxation time and defacing time?
So what you need is very fancy circuits that bundle error-prone qubits into what we call a logical qubit. So what you need is you prepare a logical state of a single qubit by hundreds of qubits. They are so-called surface codes, special kind of mechanism, how to encode them. Then you perform a gate on this bundle of physical qubits, which brings in the difficulty that a one qubit operation must be realized as a subroutine on this hundreds of physical qubits. After each step, you check whether an error occurred. This is another protocol to verify whether an error occurred. This is a protocol to derive a syndrome. And the syndrome is then basically indicating which algorithm you need to run to correct this qubit. Then the next gate comes and so on. So it's really, you blow up an algorithm significantly. This is also explained in part of the lecture that we are giving, how to do quantum error correction. So I hope I did give an answer here.
Thank you. Another question from Bernhard Brenner, who asks, if I apply C0 twice on the same qubit, I will always influence the value of Y, correct?
Again, can you repeat the question?
If I apply C0 twice on the same qubit, I will always influence the value of Y, correct?
So we have X, Y.
Yeah, X, Y, Z.
Yes.
Yeah.
Yeah. Okay, but in theory, you get the original qubit back because C0 is unitary map. C0 is the inverse of C0. So applying C0 twice results in the original state.
I think we have time for 2 or 3
A
more
couple.
questions.
I have time. I have time.
You have time. Okay. Since we can't go out for Blachuto this time, we have time for more questions.
Perfect. So then a question from Michael Koning. On your slide showing different IBM sites, the relaxation time is different for every location. What is the reason behind this? Is this due to quality differences?
Absolutely. These are quality differences in the QPUs, in the chips. And the chips are even, and the quality, the decoherence time change from hour to hour, from day to day, right? They even move to a different location because the first location, this is what colleagues from IBM US basically told me, the first location was at close to a lake where you had gooses. And if the goose were starting on the water, right, the vibration were disturbing the qubits. This is why I moved to a completely different location so that the qubits are a bit more stable.
Thank you. A question from Glenda Hannibal. Thanks for the great talk. So my question is, what exactly goes into the creation of entanglement for qubits? How is this done?
Simple answer, based on a CNOT. And how it is done, I would basically say, being only a physicist by education, this is magic, right? What happens during entanglement is not really well understood by physicists, and even philosophers are discussing what is happening. How is nature built in order to allow these very strange states like entanglement, although you can prove that most states in a quantum computer are entangled. So this is a question, maybe you can discuss a Nobel Prize winner in quantum physics, what is going on, but this is far beyond my knowledge here.
Sharam Duster would like to know what determines the decoherence time.
As I indicated, gooses that are trying to start on the lake, mesons that are coming out of outer space and come into the QPU and so on. A lot of physical phenomena are basically disturbing the different qubits.
Just a moment for questions. Bernhard Brenner would like to know, can you clearly outline the category of problem which is solution quantum computing doesn't accelerate? Can you clearly outline the category of problem whose solution quantum computing doesn't accelerate?
Cannot accelerate. So first of all, a quantum computer can solve any problem that a classical computer can solve. Based on a certain gate that's called the Toffoli gate, very easy to prove. That means a quantum computer is more powerful than a classical computer. I'm not sure. So if you take a look at complexity classes, right, you basically have the polynomial hierarchy. You have P contained in NP, then you have polynomial hierarchy, and then you have BQP that is containing P intersecting with NP, and then it contains problems that are even out of the polynomial hierarchy. So, but I can't. So I'm mumbling here. So I can't really say which kind of problems won't be speed up. Right? It's our own invention. We need to come up with algorithms. If they use entanglement, there are chances to result in a speed up. But this is innovation that is still open that we need to work on.
Okay, Vincenzo De Maio says, there's a lot of discussion about the killer app for quantum computing. What is your opinion on the topic? Also, is it possible, okay, to have the recording of the talk? Yes, it is.
Yes.
Details on the website tomorrow.
Okay, so if I would know a killer app, I would quit university and go back to industry and build the killer app. No, but what is currently done is many applications are in the area of material simulation. So we are working with an automotive company that is using simulation. I'm in touch with a couple of chemical and pharmaceutical industry that are using simulation of molecules. This is very easy because a molecule is determined by the electrons in the outer shell, right? And you need to, and the states are basically represented by eigenvalues. So what you need to do is there's a language called OpenFermion, how you describe molecules, and then you basically compute the eigenvalues to find out how to manipulate the molecules in order to have certain physical chemical properties. This is what people are already doing in practice with non-trivial molecules. What people are doing also is optimization. They use QAOA or a very different kind of hardware architecture called a quantum annealer. There's one company out, D-Wave, that is building quantum annealers. These are special quantum computers that are geared towards solving binary optimization, quadratic binary optimization problems. And they are already solved based on machine. I know a couple of companies that do classification with today's quantum computers, right, in order to find out whether goods they produced will very likely show a certain error, right? They produce something, then they measure at certain points this. So I'm not telling you what kind of good it is, because then you know what companies these are. Then they measure the particular goods, and the data are fed into a support vector machine that runs on a quantum computer, because quantum computer has something that is called a quantum kernel estimator. You can, if you know support vector machines, you know kernel methods, and then kernels can be simply much faster, much better be realized on the quantum computer, and then the result comes basically. These are some kinds of applications. And if you want to understand more, this project Planck, Planqk, has a website, planck.de. There is where we discuss use cases that are currently worked on with a bunch of industry partners.
Thank you. Then a question from Uwe Egli, who asks, how do you prepare the initial quantum state in a machine learning setting where you have a huge bunch of data? As far as I know, initial state generation is the huge problem for many applications. Do you have an improved solution to this problem?
It is the problem in quantum machine learning. There are a bunch of algorithms. So what we are doing is we prepare states of, let's say 40, 50 vectors that we do on machines that we are basically using, but this is not a huge data set. So this is in experimental state, right? You can prepare reasonable amounts of test data or training data that you use. And what we are doing in this Planck project, we are solving problems of the same size classically as well as on a quantum computer. So we solve it on a quantum computer, then we understand what the problem size is, then we solve it on a classical computer, and then we compare the precision of the results, the response time that we need to produce a result, and then we store this knowledge. Planck also has a platform where this kind of knowledge is basically stored. And we have also a tool, Johanna Bartzen, who will also be in Vienna. She built a tool where you can really compare the classical algorithms and the quantum algorithms. You describe the problem, and then you basically say, solve it with this algorithm classically, solve it quantum, and then you can literally play around with it. So this is an experimental stage we are basically on.
May I answer another question? Because there are quite a few questions from our students, which would like to attend the course of Frank Leymann. You know, you can apply, then you are on a waiting list, and we will make, we will find a solution so that at least most of you can attend the course. Yeah? Because I guess most of you only want to attend the course and don't need really a very difficult exam, so we will find a solution on that. Thank you.
Okay.
Okay, then let's.
I would say last question, if this is okay. Yeah, also for you, Frank, I think it's
fine.
So then this very interesting question from Andre Brichter, who asks, can we use entangled qubits for communication without existing network and networks and without distance-based latency?
Distance-based?
Latency.
So now you need to repeat the question again.
Okay. Can we use entangled qubits for communication without existing networks and without distance-based latency?
Without existing
Probably.
So maybe the person may speak up and try, somehow reformulate the question.
Okay.
So what I know is that in Vienna, Anton Zeilinger basically made the first teleportation experiments in Vienna over a couple of kilometers. He did teleportation, which does require entanglement. These days, the Chinese researchers have teleportation and symmetric key exchange via satellite and laser lines between different cities in China. This doesn't answer the question, but this is to give you an impression what is currently done in communication based on quantum bits and entanglement. And yeah, okay.
Exactly. And I think this was even done between China and Vienna also, a couple of...
Oh, recently. Oh, I didn't know that. Ah, good.
Yeah, that Zeilinger...
Yeah, Anton Zeilinger, very famous,
Anton
right?
Zeilinger, of course, with his kind of colleague, also the president of the Academy of Science in China, and they were using satellite communication, as you were just saying, to demonstrate
Absolutely.
Their results. You know, again, Frank, it was really amazing, all the information. Yeah? I guess we need at least a couple of days to digest all this information. We will all go to your course. It will be also recorded, so it is possible to attend. And as I already said, I'm really looking forward to have you really physically, not only, you know, kind of in a virtual world, to have you physically and your colleague in Vienna, and to continue our collaboration. Thank you also to the audience. I really, excuse me, when I just continue, thank you also to the audience for attending our public lecture of our first Kurt Gödel Visiting Professor. And I can assure you we will continue with this great person. Thank you, Frank.
You have a good time. Bye.
Bye-bye.